In this video, I'm going to talk about another integration strategy where we use partial fraction decomposition, our old friend from back in the day that we'd never use. So I've got this integral here of dx over x squared plus x minus 2, and I'm trying to integrate it. And I can tell u sub is not going to work. And with the quadratic down below, we may be thinking inverse trig function, but they don't quite line up nicely. Oh yeah, we could try to complete the square in order to set it up that way, but we use completing the square when we can't factor the denominator. This denominator is factorable. I can rewrite this as the integral of dx over the product of x and a 2 and 1. The signs are different, and the bigger one needs to be positive. So x plus 2 and x minus 1. So this integrand, dx over that product, I can rewrite this using partial fraction decomposition. In fact, I'm going to put my red pen away for a little bit, leaving integration land. I'm just going to look at my integrand, and I'm going to rewrite it. So I'll do that in blue. I have the fraction 1 over x plus 2 times x minus 1. And I claim if I have the fraction of, or where the denominator is two different factors, then that must have come from the addition of two things being added together, where that was the common denominator. I mean, I don't know what a was, but some number over x plus 2 being added to some other number over x minus 1. If I was given the right-hand side of the equation, these two fractions, when I add them together, I would need to go off and get a common denominator. The common denominator would be their product. Bam. So I just need to figure out what values a and b would make this true. Okay, well, I can do that. What I'm going to do is I'm going to take this equation and I'm going to multiply through by the LCD, the least common denominator, and that is these two being multiplied together. I'll bust out another color to help me showcase this. It is legal to multiply the left-hand side of an equation as long as I do it to the right-hand side as well. And I'm just going to multiply everything by that LCD. This is going to eliminate my denominators because on the left I have a lot of reduction. It just reduces to 1. On the right, with my a term, the x plus 2 factors will reduce, and I can multiply a times x minus 1. Similarly, I'll have b times x plus 2. I'll go ahead and do the distribution. Ax minus a plus bx plus 2b. And I'm going to get the like terms together. That is, I'm going to get my x variables together. Just manipulating. Hopefully you're agreeing with all the legality of this. Now, I think what I'd like to do is just see the term that's being multiplied by x. So that is, I'm going to factor an x from these two terms, but I'm going to not write it in front, I'm going to write it behind, like so. You agree if I were to distribute the x, I would have ax plus bx. So I've just factored out that x and I've written it in this way. Now I've done that because this is an equation. The left-hand side of the equation must equal the right-hand side of the equation. They are equal. So on the right, I've got some constant over here, this negative a plus 2b. These are just numbers being added together. That must equal this constant 1. And then the x term has to equal the x term on the left-hand side of the equation. Well, there's an x term there. Can you see it? Maybe if I write it as 0x plus the constant. So I have some x term and some constant, and those are equal to each other. I'm going to write those two as being equal to each other. So I claim 0x must be equal to a plus bx. 0 must be a plus b. And then the constant 1 must be equal to negative a plus 2b. What I've created here is a 2x2 system, or a system of two equations with two unknowns. There's lots of ways to solve this. You could even use matrices, Gauss-Jordan, elimination. I'm just going to use substitution. These look so nice. In fact, if a and b equals 0, I could solve that equation for a. A must be equal to a negative b. If I subtract that over, I can then take that negative b and plug it in place of a into the second equation. So I'm rewriting the second equation. 1 is equal to negative a, but a is just negative b. Well, negative b is positive. That looks like a 3b. So then 1/3 equals b. Oh, and I know a in terms of b. If b is 1/3, then a would be negative 1/3. All right. So I claim I can then plug those back into this sum up here. And in fact, let me just kind of do that real quick, maybe to help us out. Different color. So we have negative 1/3 over x plus 2 plus 1/3 over x minus 1. Oops, you can't see that. If you take those two fractions and you add them together, that is, you get a common denominator, you add them together, you'll end up with 1 over the product of x plus 2 and x minus 1. So I'm going to go back to my integration problem, and I'm going to rewrite this as that fraction being split up. Come on, there we go. All right, I claim it's going to be, I'll put that positive first. 1/3 over the x minus 1 factor, and then we're adding that negative 1/3. So I'm going to say minus 1/3 over the x plus 2 factor. So I used partial fraction decomposition to take that original integrand and separate it into the difference of these two fractions. And this is very convenient because though I couldn't integrate the integrand here, now I have the integral of two different things, the difference, and I can bust up that integration. So this is the integral of the first one minus the integral of the second one. In both of these integrals, I can pull out the 1/3, and then this is just the natural log. You can use u substitution if you need to. You'd have 1 over u, which is the natural log of u, and there's no sort of like chain rule involved. I think we're comfortable doing this. 1/3 natural log x minus 1 minus 1/3 natural log x plus 2 plus c. I'm looking at the answer. I'd have to give you full credit for that. There is, because of the natural logs, we could do some manipulation, maybe simplification. The common 1/3 I can pull out. And if you have the difference of two logs, you could rewrite that as a single log using some division. You could even, because now I have a coefficient on a single log, I could even rewrite that as a power if I wanted to, using that log power rule. I don't know, we got to stop somewhere, and that looks good. All of these are really good final answers there. All right, let's try that again. Partial fraction decomposition. This is something we should have learned in a previous class, but most of my students in Calculus 2, they didn't use it enough, so they need to see it in action again. So just wanted to walk through the process. You take your fraction and you say, hey, it's got to be the sum of different fractions. So if I had another factor, I would just have a third fraction here, a, b, and c. And you just do this same process. And let's do it again. I can amp up the difficulty, though, by adding a new issue that can arise. Let's take a look at this example. The integral of 2 over x cubed plus x squared. Now, don't pause the video and try this on your own. There's something new here. U substitution fails me. It does not look like arc tangent, no, but I can at least factor it. I can pull an x squared from the denominator. I could even pull that 2 out, but I didn't do it yet. This integrand has something called a repeated factor. I have x times x times x plus 1. You have to account for that repeated factor when you set up the partial fraction decomposition. So again, I'm going to change color here, stepping away from the integration. I'm going to play around with just this fraction. 2 over x times x times x plus 1. When we set up the PFD, partial fraction decomposition, we need the x plus 1 clearly. We then need to use x to the first power and then an x to the second power. You need to show every power up until the highest power. So if this were x to the mth power, I would need x to the first, an x to the second, plus an x to the third, plus an x to the fourth, plus an x to the fifth, dot, 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 plus x to the mth power. This is a repeated factor. You need to show all the powers leading up to it. All right. Now we just kind of go through the same motion. I need to multiply through here to get rid of the denominator. You can multiply through by the LCD. You don't need to multiply by x and x squared or like an x cubed, that's overkill. Just do the x squared. That's going to eliminate those x's terms, and you need the x plus 1 to get rid of this. What am I doing? This is not a square. That's an x plus 1. This is an x plus 1. I have an x squared and an x plus 1. Just multiplying by x squared, x plus 1. Okay. On the left, things reduce, leaving me with just the 2. On the a term, the x plus 1 will reduce, but I'm left with ax squared. On the b term, one of the x's reduce, leaving me with bx x plus 1. On the c term, all of the x's reduce, leaving me with c times x plus 1. All right, like last time, I'm going to go ahead and distribute, and then I'm going to get all the like terms together. So I'll get all the squares together, the x's together. And any constant. I'm going to get that together. So it looks like I have, they're already together. So from the a and b, I can pull out an x squared. From this bx and cx, I can pull out an x. And we'll go ahead and do that. So from the two terms with the quadratic term, I pulled out the x squared, leaving me with a plus b. From these next two terms, I can pull out an x, leaving me with b plus c. Plus a 1 all by itself. And again, this is an equal sign. So the left-hand side must equal the right-hand side. So it's clear to me that my I've got some sort of quadratic term over here. Maybe you want to call that 0x squared. And I've got some sort of linear term. Maybe you want to call that 0x. I'm going to set the coefficients equal to each other. So the coefficients of the quadratic term, the coefficients of the linear term, and then these constants. Those don't make any sense, but I'm going to just play with this. Okay. So let's see. That sounds really weird. Oh. Okay, yeah, good. I was like, 2 does not equal 1, but I've got it here. I can't multiply. C times 1 is 1c. Okay, now it's going to make sense to me. Coefficients equal, and the 2 must be whatever this constant is over here. And this time I only have the variable c, so I know that 2 is c. But I'm going to set up 3 equations. 0 must equal a plus b. The coefficient of the linear term must equal b plus c. And my constant must equal the constant c. Alright, well if I know that c is 2, then I can plug c into this equation. 0 is equal to b plus 2, or b is equal to negative 2. And if I know b is negative 2, I can plug it into this equation. 0 equals a plus a negative 2, Add that over. A is equal to 2. So I know my A value, I know my B value, and I know my C value. I can go back up here and I can plug in my A, my B, and my C. I'm going to rewrite my integral as the sum of these three fractions, and I know A, B, and C now. A over x plus 1, where A is 2. B over x, where B is negative 2. C over x squared, where C is 2. This is extremely powerful because now I can bust this up into 3 separate integrals. I think also in this step, I'm going to pull out all of these coefficients. So I should have 2 times the integral of dx over x plus 1 minus 2 times the integral of dx over x plus 2 times the integral of dx over x squared. Well, the first two are natural logs. This one is the same thing as x to the negative second power, so I can use a power rule for integration. So here we go. I think I can fit it on this page. This is going to be 2 times the natural log of x plus 1 minus 2 times the natural log of x. Now here, I'll go ahead and write down the plus 2. The power is increased by 1, so it's going to go to the negative first power, and then you multiply out front by the reciprocal of that new power. So there's this negative 1 factor out front as well. That's going to make that minus 2 over x. And like the previous problem, because of the multiple natural logs, we could maybe play with it a little bit. I like that answer. I do see the common 2 though, and I see another difference. That's another good stopping point there. All right. So just another strategy for integration. If you're able to factor the denominator, then you could break up that factor using partial fraction decomposition. And with parts of it, it should be easier to integrate. All right, go try some homework, and I'll see you in the next video.